from EC department. So we have gathered here to discuss the case study topic, design and analysis of low power full ladder using CMOS technology. So we can discuss from introduction to what is the importance and performance. Everything we can discuss.
Hello everyone, I'm going to talk about the introduction and objective of the case study. Full adder is a key arithmetic logic where it is widely used in ALUs, multipliers, and various fields, and it is the main processor of the main logic where it uses logic gates for the designing, and it is also useful for power consumption and power reduction, and it is by critical of portable and for high performance language. An objective, we are going to see about the low power high full ladder for CMOS logic. In that, we are reducing the transistors for the area consumption. We have to reduce the areas where we can. It will be so easier for the building or designing a chip or a circuit, and it is also implemented in various fields where VLSI scaling is used in this. The process of scaling is consuming the energy consumption and reducing the power of the circuit.
So I would like to talk about the CMOS technology and basic for full ladder, basic of full ladders. And the CMOS technology, CMOS first basically is CMOS combines PMOS and NMOS transistors and is used to designing your logic circuits. And then the main advantage of the CMOS is it uses the uses for the modern electronic items like for efficiency. And then the second advantage is it's used with the low static power consumption, and also the third is dynamic power. Dynamic power used to is caused by the charging of capacitance and discharging of capacitance by over switching the circuits. And then it increases the frequency of the circuit, and also there are some parameters which is used in the circuit is threshold voltage and supply voltage, and also capacitance and also frequency. And then moving to the full adder basics, the full adder basics of the arithmetic operation is three inputs in A and B and C carry in. So and the outputs are sum and carry out, and the A and B are XOR gates, and carry in it's the sum of the elements, and then the outputs are carry out. So sum and carry out, and sum is the carry out is a majority in the expression called AB plus B carry in plus C and C carry in and A. So this is the expression of the full adder. So and then and also the CMOS is the backbone for the modern digital signal processing, and also and we understanding the applications like full adder is more important and vital for the experiment, and also it have a high performance chip design.
Now let's have a look at some design approaches and optimization technique in digital circuit. First, we have a conventional CMOS design. We need to implement this using around 28 transistors to make a basic logic gates. And here it consumes more power and more space, but it isn't ideal for today's compact and power efficient devices. So to tackle this, we use some optimization techniques like pass transistor logic, which reduces the number of transistors used and the area needed. And next, transmission gate logic, which cut down the power or speed and the complexity. And next, the gate diffusion input. It's a modern technique that supports the strong signal transfer and the low power usage. So we can, and in some designs, we can use hybrid approaches by combining these styles to get a best balance of speed, power, and the size and the complexity. For example, an optimized full adder can be made with just 10 to 14 transistors, uh, while it's still working with accuracy and the power saving.
Okay, coming to the analysis and the simulation setup, the optimized version of full adder is simulated using the standard VLSI tools like DSCH, Cadence, Microwind, etc. And the technology node selected for the implantation is the 90 nm CMOS with voltage of 1.8 voltage, and the it is tested with the clock frequency of 100 megahertz and the capacitance of 10 femtofarads. The power saving, chip area size, and the propagation delay were mainly concentrated in the uh, conventional for adder, it has 28 transistors and it consumes more power due to the huge gates, and comparing with the GDI, the latest version, the transistors are less and the power consumption is less.
Coming for the last part, application and the conclusion part. On application, optimized low power adder takes a crucial part in embedded system, DSP, and IoT devices, power battery based devices. Where in these types and all, energy efficiency is a key, right? And coming for the benefit part, takes it reduces the size in chip, it reduces the thermal output, and mainly the cost effective in large scale industries, which makes the battery to more days, and it extends the power, so it's the main use. So coming for the challenging part, the main and foremost thing is power consumption. When we are using with a large number, that is processors, it consumed and helps with a lot of things. And foremost thing, the conclusion part, adder takes a crucial part in embedded system and digital systems, for small scale industries, while coming for large size, to overcome the delay in power consumption is more.
After this long discussion, basic circuits like a adder, multiplier, everything is very very important in this electronic circuits. So, by using this low power technology, we can design more and more circuit for better efficiency, so that, as said by Vijay Krishna, so the battery usage will be improved. Vast applications in digital DSP, so everywhere it is used. So this is a very much important technology that we need to implement in every circuit design. Thank you all for joining this video.